Hello there, and welcome to Snoozing Ideas channel. I'm so glad you're here tonight. Whether you've had a day that stretched your mind to its limits, or you're simply seeking a peaceful transition into dreams, you've found the perfect place to rest your thoughts. Allow your shoulders to soften now, your breath to deepen, and your mind to gently release the day's concerns, like leaves drifting down a quiet stream. Tonight, we're journeying through the fascinating landscape of your sleeping brain, that mysterious realm where neurons whisper in the darkness and memories dance into new formations. In 100 Facts About the Sleeping Brain, we'll explore the extraordinary neuroscience of slumber, learning how your mind transforms while your consciousness drifts. The wonders happening beneath your closed eyelids are more magical than any dream itself. Let's begin. Theta waves dance between wakefulness and dreams, marking our transition into sleep. These gentle oscillations, occurring at frequencies of 4 to 8 Hertz, emerge as consciousness begins to loosen its grip on the mind. Scientists can observe these waves through electroencephalography, tracking the precise moment when our thoughts start to dissolve into the early stages of slumber. Though widely documented, researchers still debate exactly how these rhythmic patterns facilitate the complex handoff between conscious and unconscious states. What other signals might we be missing in this delicate threshold? Like twilight between day and night, theta waves occupy that mysterious borderland where awareness gradually surrenders to the quiet depths of sleep. Sleep claims a third of our existence on this planet. Through the quiet nights that punctuate our days, we spend approximately 26 years of a 78-year life, with eyes closed and consciousness adrift. This substantial portion of our lives unfolds in cycles of rest that restore body and mind. Scientists have documented this universal need across cultures and throughout history, finding that humans consistently dedicate this significant fraction of time to sleep. The necessity appears non-negotiable, woven into our biology at the deepest level. Like breathing or the beating of our heart, sleep occupies its rightful share of our journey, a recurring sanctuary in the timeline of our lives. The suprachiasmatic nucleus orchestrates the rhythm of our days and nights. Nestled within the hypothalamus, this tiny cluster of roughly 20,000 specialized neurons serves as the body's master timekeeper. It receives direct input from light-sensitive cells in the retina, allowing it to synchronize internal processes with the rising and setting sun. Researchers have found that damaging this small region disrupts the entire body's sense of time. Though remarkably precise, this biological clock occasionally drifts out of alignment with the external world. Is this why jet lag feels so profoundly disorienting? Like a conductor leading a vast biological orchestra, the suprachiasmatic nucleus keeps each cellular instrument playing in harmony with Earth's rotation. During REM sleep, the brain awakens while the body remains still. In this paradoxical state, oxygen consumption increases by 20% compared to quiet wakefulness, revealing intense neural activity beneath closed eyelids. Researchers measuring cerebral blood flow have documented this surprising metabolic surge during the very phase when we seem most disconnected from the world. The brain burns energy at levels comparable to active thinking, yet consciousness remains suspended in the realm of dreams. This heightened activity suggests that important work happens during these periods, perhaps organizing memories or processing emotions. Like a city that comes alive after dark, the sleeping brain reveals its hidden industry when the conscious mind has stepped away. Memories find their permanent home during deep sleep. As we drift through slow-wave slumber, information transfers from the temporary storage of the hippocampus to the more permanent archives of the neocortex. This consolidation process strengthens important neural connections while pruning away less significant details. Neuroscientists can observe this activity through specialized brain imaging techniques, watching as yesterday's experiences become tomorrow's long-term memories. Though we appear inactive, this crucial filing system operates most efficiently when consciousness is fully suspended. The quiet hours of night serve as the library's cataloging time, where fleeting experiences are carefully preserved in the vast volumes of our mind. The sleeping brain cleans itself more thoroughly than when awake. During slumber, the glymphatic system increases its activity by 60%, creating a remarkable waste clearance mechanism unique to the central nervous system. Cerebrospinal fluid flows more freely between cells, removing accumulated proteins and metabolic byproducts that build up during conscious hours. Researchers using specialized imaging can actually visualize this enhanced cleansing process in action. Why this system requires unconsciousness to function optimally remains partially unexplained. Like a city's maintenance crews that work best when streets are empty, the brain's cleaning system takes advantage of neural quietude to perform its essential housekeeping. Adenosine gently pulls us towards sleep with increasing insistence throughout the day. This neurochemical gradually accumulates in the brain during wakefulness, building what scientists call sleep pressure over approximately 16 hours of consciousness. Caffeine works precisely by blocking the receptors that would normally respond to this compound. Researchers have mapped how adenosine levels rise predictably with each waking hour, creating an elegantly simple timer that eventually makes staying awake nearly impossible. Like sand filling an hourglass, adenosine measures out our capacity for wakefulness until the inevitable moment when we must turn over and begin again. The sleeping mind travels through landscapes of varying depths. Each night, the average sleep cycle carries us through distinct stages lasting between 90 and 110 minutes, repeating 4 to 6 times in healthy adults. Scientists tracking brain waves can identify precise transitions between lighter and deeper states as the night progresses. These rhythmic journeys appear remarkably consistent across cultures and age groups, though their quality and duration can be influenced by numerous factors. Could these cycles reflect ancient patterns synchronized with natural rhythms we've long forgotten? Like ocean tides that rise and fall with predictable grace, the sleeping brain follows its own timeless choreography through the quiet hours. The brain cools itself during deep sleep. Body temperature drops by 1 to 2 degrees Celsius during non-REM stages, a subtle yet significant change that scientists believe supports optimal neural recovery. This cooling coincides precisely with periods of slowest brainwave activity. Thermal imaging reveals this temperature decrease affects brain tissue more dramatically than other body regions. Though seemingly minor, this temperature shift creates conditions necessary for specific maintenance processes that cannot occur in warmer states. Like a computer that performs better when its components are cooled, the brain appears to optimize certain functions by slightly lowering its thermal state during its deepest rest. The thalamus stands guard over the sleeping mind. Acting as a vigilant gatekeeper, this structure reduces incoming sensory information to the cortex by up to 90% during deep sleep stages. Scientists studying neural pathways have traced how this filtering mechanism allows the brain to maintain unconsciousness even in environments with moderate noise or light. The thalamus essentially disconnects higher processing centers from external stimuli, though it remains selective about which signals to block. important or dangerous sounds might still break through. Like a nightclub bouncer who decides which guests may enter, the thalamus protects sleep's fragile territory from unnecessary disturbance. Slow-wave sleep silently diminishes as we age. This deepest form of non-REM sleep occupies between 20 to 25% of total sleep time in young adults, but gradually decreases with each passing decade. Researchers tracking thousands of sleepers have documented this consistent decline across populations. The reduction occurs even in healthy individuals with no sleep complaints, suggesting it represents a normal aspect of brain maturation. The reasons for this change remain incompletely understood, though it correlates with changes in memory and cognitive processing. Like shadows that lengthen with the setting sun, our relationship with deep sleep shifts almost imperceptibly as our years accumulate. The pons orchestrates our dreams from deep within the brain. Located in the brain stem, this region generates REM sleep through carefully timed acetylcholine release from specific neuronal populations. Scientists studying this structure have identified how it simultaneously paralyzes the body while activating visual centers in the cortex. This elegant system explains why we experience vivid imagery, yet remain motionless during dreams. The evolutionary purpose of this complex neurological dance has inspired numerous theories, but remains incompletely resolved. Could these mechanisms serve purposes beyond what we currently understand? Like an unseen puppeteer controlling both the show and the audience's response, the pons creates dreamscapes while ensuring we remain safely inactive. Sleep spindles flicker like distant lightning across the sleeping brain. These brief bursts of neural activity, lasting just half to 2 seconds each, occur every 3 to 10 seconds during stage 2 non-REM sleep. Electroencephalograms reveal their distinctive pattern, a rapid increase and decrease in frequency that creates their spindle-shaped appearance on recordings. Neuroscientists have linked these oscillations to memory consolidation and protection from disturbing stimuli. Though fleeting, each spindle represents thousands of neurons firing in synchronized patterns across different brain regions. Like brief communications between distant parts of a vast network, these ephemeral signals help organize the day's experiences into coherent memories. The default mode network awakens during REM sleep. This collection of brain regions, typically active during daydreaming or self-reflection, shows increased connectivity during dream states compared to wakefulness. Brain imaging studies reveal striking similarities between the patterns of activation during introspective thought and those that emerge during REM sleep. This unexpected finding suggests dreams may serve similar psychological functions as conscious contemplation. Scientists continue exploring why this network, associated with our sense of self, becomes particularly active when consciousness is suspended. Like an actor who performs differently when the theater lights dim, the default mode network may reveal its truest nature when we're no longer watching. Melatonin begins its gentle cascade approximately 2 hours before natural bedtime. This hormone flows from the pineal gland in response to decreasing light, signaling to countless cells that darkness has arrived. Researchers tracking its daily rhythm have documented how artificial light can delay or diminish this natural flow. The timing of this release varies between individuals, helping explain why some people naturally prefer earlier or later sleep schedules. Though well studied, the subtle interactions between melatonin and other circadian signals continue revealing new complexities. Like the first raindrops before a shower, melatonin molecules begin falling through the bloodstream, preparing body and mind for the approaching night. The locus coeruleus falls completely silent during REM sleep. This small nucleus, containing the brain's primary source of norepinephrine neurons, becomes utterly inactive during dreaming states. Neuroscientists measuring its activity have documented this remarkable shutdown, which contrasts with its steady activity during wakefulness and non-REM sleep. This chemical silence may explain the bizarre, illogical nature of dreams. Without norepinephrine's reality-checking function, the mind accepts strange scenarios without question. Like a skeptical voice that suddenly goes quiet, the locus coeruleus stops providing its usual voice of reason, allowing dreams to unfold according to their own peculiar logic. Cortisol follows the contours of night and day within our bloodstream. This stress hormone reaches its lowest concentration around midnight and begins a gradual rise approximately 2 to 3 hours before natural awakening. Researchers tracking its daily rhythm have found this pattern persists even in constant darkness, revealing its deep connection to our internal clock. The precise timing of this hormonal shift prepares the body for the energy demands of waking. Though invisible to our conscious awareness, this biochemical tide influences everything from metabolism to immune function. Like a tide that rises before dawn, cortisol flows through sleeping vessels, preparing shores of consciousness for the approaching day. The sleeping brain processes an ocean of information while consciousness rests. During slumber, approximately 11 million bits of sensory data flow through neural pathways, yet only about 40 bits register in any meaningful way. Neuroscientists measuring brain responses have documented this remarkable filtering capability, which allows important signals to break through while dismissing countless irrelevant details. This selective attention explains why a mother might sleep through traffic noise, yet wake instantly to her baby's cry. What criteria does the brain use to determine which 40 bits matter most? Like a discerning editor scanning endless text for just the perfect phrase, the sleeping brain evaluates millions of inputs to find the few worthy of response. Delta waves dominate the landscape of deep sleep. These slow oscillations, ranging from just half to 4 Hz, characterize the most restorative stages of non-REM sleep. Electroencephalography reveals these powerful waves sweeping across the cortex, their amplitude far exceeding the smaller, faster patterns of lighter sleep or wakefulness. Researchers have correlated the presence of these waves with the body's most intensive repair processes. Though we experience nothing of these waves consciously, they create the conditions necessary for physical restoration. Like great ocean swells that rise and fall with majestic slowness, delta waves move through neural tissue, carrying the mind to its deepest underwater realms. Sleep deprivation starves the thinking brain. When we go without adequate rest, glucose metabolism in the prefrontal cortex decreases by up to 40%, essentially restricting fuel to the very regions responsible for complex thought and decision-making. Brain imaging studies clearly reveal these metabolic deficits following even one night of poor sleep. This energy reduction explains why sleep-deprived individuals struggle with tasks requiring planning or impulse control. Though other brain regions show similar but less dramatic effects, the prefrontal areas suffer disproportionately. What critical functions might be compromised by this selective impairment? Like a power reduction affecting the executive floor of a company, sleep loss impacts the brain's highest control centers first. The pineal gland transforms day into night through biochemical twilight. This small pine cone-shaped organ produces melatonin at rates 10 to 15 times higher during darkness than in daylight, creating a powerful internal signal of nighttime. Scientists measuring this hormone in the bloodstream can precisely track its dramatic rise and fall with each day-night cycle. This ancient chemical messenger has remained remarkably consistent across species throughout evolution. Though easily disrupted by artificial light, the pattern reasserts itself when natural conditions return. Could this biological rhythm be more fundamental than we realize? Like a faithful timekeeper that has measured darkness since life began, melatonin marks the boundary between our waking and sleeping worlds. REM sleep episodes grow longer as night transitions toward morning. Beginning with brief visits of just a few minutes, these dream-rich periods gradually extend to 30 or even 60 minutes during the final sleep cycles before awakening. Researchers tracking thousands of sleepers have documented this consistent pattern across age groups and cultures. This architecture suggests the brain prioritizes different activities at different points in the sleep period, perhaps completing physical restoration before turning to psychological processing. Though we remain unaware of this shifting schedule, it follows a remarkably precise timetable. Like movements in a symphony that grow more complex as the piece progresses, REM periods expand and elaborate as night advances toward dawn. The dreaming brain mimics wakefulness while the body lies still. Electrical activity during REM sleep closely resembles patterns observed during active consciousness, creating what scientists call paradoxical sleep. EEG recordings reveal fast, irregular waves nearly indistinguishable from those of an alert mind actively processing information. This striking similarity suggests dreams engage many of the same neural networks used during waking thought. Researchers continue exploring why evolution would preserve this energetically expensive state across so many species. Like an actor rehearsing lines when the theater is empty, the brain may use this time to practice important neural performances without real-world consequences. Sleep architecture follows a predictable journey across the human lifespan. The deep, slow-wave sleep that fills the nights of childhood gradually diminishes, decreasing by approximately 2% per decade after age 30. Scientists tracking sleep patterns across age groups have documented this consistent decline in thousands of individuals. This architectural shift occurs independently of sleep disorders or health conditions, appearing to represent a normal aspect of brain maturation. The biological purpose behind this change remains the subject of ongoing research. Do our brains simply need less restoration as we age? Like a house that requires different maintenance as it weathers the years? The sleeping brain adjusts its renewal processes as we grow older. The reticular activating system holds the keys to consciousness itself. This diffuse network of neurons coordinates the delicate transition between sleep and wakefulness through multiple neurotransmitter pathways. Researchers studying this system have identified how it receives and integrates signals from throughout the body before determining whether to maintain sleep or trigger awakening. Damage to this region can result in profound disorders of consciousness, highlighting its fundamental importance. The complexity of this switching mechanism reflects the critical nature of properly timing these state transitions. Like a master control panel with countless dials and switches, the reticular activating system manages the precise thresholds between our conscious and unconscious hours. Protein synthesis accelerates while consciousness rests. During slow-wave sleep, Neurons increase their production of essential proteins by 30 to 50% compared to waking states. Scientists measuring molecular activity have documented this dramatic upregulation of cellular machinery during the deepest sleep phases. These newly constructed proteins support everything from memory formation to cellular repair and growth. The brain appears to strategically allocate its resources, prioritizing outward responsiveness during the day and internal maintenance at night. Though invisible to observation, this molecular industry represents some of the most important work occurring during sleep. Like a factory that shifts to its most intensive production after visitors have gone, the sleeping brain constructs its essential components during quiet hours. The sleeping mind maintains a selective vigilance against the darkness. Even in deep slumber, the brain preserves its ability to monitor environmental sounds, responding to personally significant noises, like one's name being called. Researchers testing this phenomenon have documented how specific auditory stimuli can activate processing regions without causing full awakening. This selective attention represents an elegant evolutionary adaptation, allowing rest while maintaining awareness of potential threats or important signals. The mechanisms behind this discriminative capability remain incompletely understood. Like a night watchman who ignores routine noises but responds immediately to anything unusual, the sleeping brain maintains just enough awareness to protect its vulnerable state. GABA neurons actively impose the state of sleep upon the reluctant brain. Located in the ventrolateral preoptic nucleus, these specialized cells release inhibitory neurotransmitters that systematically suppress wake-promoting regions throughout the nervous system. Researchers have traced the connections of these neurons as they extend to arousal centers, documenting how their activation leads directly to sleep onset. This discovery reversed older views that sleep occurred simply from exhaustion of waking systems. Instead, sleep represents an actively regulated state, not merely the absence of wakefulness. Like a skilled hypnotist quieting a room full of active participants, these GABA neurons progressively silence the brain's many voices until consciousness gently slips away. Sleep-related memory consolidation unfolds at accelerated speed. During this process, neural firing patterns from daytime learning experiences replay at 6 to 7 times their original pace, allowing efficient integration of new information. Researchers recording hippocampal activity have captured these compressed rehearsals occurring during specific sleep stages. This acceleration explains how the brain can process vast amounts of experience during limited sleep periods. Though we perceive nothing of this high-speed review, it strengthens the connections that form our memories. What determines which experiences receive this special treatment? Like a video editor working through footage at high speed, the sleeping brain rapidly reviews the day's events, deciding what merits preservation in its permanent archive. Dreams visit us more frequently than we realize. The average person experiences 4 to 6 distinct dream episodes each night, though most vanish from memory shortly after awakening. Researchers studying sleep in laboratory settings have documented these numerous dream periods by waking participants during different phases of sleep. The content appears to vary throughout the night, with earlier dreams often reflecting recent experiences, while later dreams become more emotionally complex and bizarre. The rapid forgetting of these experiences suggests they may serve their purpose without requiring conscious recall. Like footprints on a beach that wash away with the tide, these nighttime narratives leave their impression on the mind, even as their details dissolve with morning light. Brain-derived neurotrophic factor flows abundantly during our deepest slumber. This remarkable growth protein, essential for forming new neural connections, reaches peak expression during slow-wave sleep. Scientists measuring its presence in cerebrospinal fluid have documented this surge, which correlates precisely with periods of delta wave activity. This timing suggests the brain strategically schedules its most intensive growth and repair work during specific sleep phases. Though invisible to observation, this molecular cascade supports everything from daily learning to recovery from injury. What critical maintenance might we compromise when sleep is cut short? Like a gardener who waters only at night, the brain delivers its most nourishing growth factors when consciousness has retreated. The sleeping brain registers information without conscious awareness. During slumber, the mind can process and respond to external stimuli, even while forming no retrievable memories of these interactions. Researchers testing this phenomenon have documented responses to odors, sounds, and even complex verbal instructions delivered during specific sleep stages. This unconscious processing explains how external events sometimes influence dreams without causing awakening. The boundaries between perception and awareness become surprisingly porous during certain sleep phases. Like a computer running background processes while the screen remains dark, the sleeping brain continues evaluating selected inputs from the outside world, all while consciousness remains suspended in its nightly pause. Cerebrospinal fluid flows more freely during unconscious hours. This clear liquid increases its circulation by 60% during non-REM sleep, creating enhanced pathways for waste clearance through the brain's glymphatic system. Advanced imaging techniques have allowed scientists to visualize this dramatic increase in fluid movement between cellular spaces. The pulsations that drive this flow appear synchronized with specific brainwave patterns characteristic of deep sleep. Though we feel nothing of this internal cleansing, it represents one of sleep's most essential restorative functions. Like a city's water system that increases pressure during off-peak hours, the brain enhances its internal currents when cognitive demands have subsided. Between worlds, we hover in delicate transition. Sleep onset typically occurs within 10 to 20 minutes in healthy individuals under optimal conditions, though we rarely notice this gentle descent. This interval, the time between closing our eyes and surrendering consciousness, represents a carefully calibrated process, neither too quick nor too prolonged. Sleep scientists measure this period in laboratories, noting how disruptions to this timeline often signal underlying sleep disorders. The threshold between waking and sleep remains porous, allowing brief returns to awareness before the final surrender. In this liminal space, thoughts soften their edges and logic releases its grip, while somewhere beneath, the quiet machinery of rest begins its nightly reset. Images flicker and dissolve at the edge of sleep. The hypnagogic state, lasting just 5 to 10 minutes, forms a strange borderland between consciousness and slumber. During this brief transition, the brain generates fragments of dreams while still partially awake, geometric patterns, floating sensations, or brief scenes without narrative. Researchers studying this phenomenon find it occurs precisely when brain waves begin shifting from alpha to theta rhythms. Neither fully asleep nor truly awake, the mind temporarily inhabits both worlds simultaneously. What purpose might these ephemeral visions serve? Perhaps they are merely neural static, the mind's gentle static as it changes channels from the broadcast of day to the quiet station of night. Wakefulness requires active maintenance, not merely the absence of sleep. Deep within the lateral hypothalamus, specialized orexin neurons continuously work to keep consciousness intact. These cells release their namesake neurotransmitter throughout waking hours, maintaining the brain's aroused state through complex signaling pathways. During sleep, these neurons fall quiet, their activity deliberately suppressed by sleep-promoting regions. The discovery of this system revolutionized our understanding of narcolepsy, a disorder where orexin signaling fails. In the intricate balance between awareness and unconsciousness, these cells stand as quiet sentinels, their whispered chemical signals holding back the ever-present tide of sleep until the appropriate time arrives. Neural conversations quiet as consciousness fades away. The sleeping brain exhibits dramatically decreased connectivity between the thalamus and cortical regions during deep sleep, temporarily severing the dialogue between these critical structures. Neuroimaging reveals how these communication pathways, bustling with activity during wakefulness, grow increasingly silent as sleep deepens. This functional disconnection explains our reduced awareness of external stimuli during slumber. Yet this separation is never complete as certain channels remain partially open, maintaining the brain's most essential monitoring capabilities. Like distant islands that were once connected by bridges now submerged at high tide, these neural territories maintain their separate existence until morning light lowers the waters once again. Each hour of lost sleep leaves an invisible debt in the body's ledger. Sleep debt accumulates at approximately 25% for each hour missed below optimal duration, creating a biological deficit that demands repayment. This mathematical relationship explains why a few nights of insufficient rest can lead to significant impairment. Scientists measuring attention and reaction time can quantify this accumulating burden with remarkable precision. Though we cannot see this mounting debt, our bodies track it faithfully, eventually extracting payment through decreased performance or involuntary micro-sleeps. What invisible calculations determine how this debt must be repaid? Like a tide that must eventually return to shore, sleep reclaims its territory with quiet but undeniable persistence. The dreaming brain suspends its voice of reason. During REM sleep, the ventromedial prefrontal cortex, responsible for emotional regulation and logical analysis, shows dramatically reduced activity. This neural quieting explains why dream scenarios that would seem absurd during wakefulness feel entirely reasonable while we're experiencing them. Researchers tracking blood flow patterns have documented how this rational center goes offline precisely when dream content becomes most bizarre and emotionally charged. Without this region's reality-checking function, the dreaming mind accepts flying, time travel, or conversations with the long-departed without question. In sleep's gentle domain, the laws of reason briefly surrender their authority, allowing experience to flow unconstrained by the boundaries of the possible. Sudden waves of electrical silence sweep across the sleeping mind. K-complexes, lasting up to 2 seconds each, represent the largest amplitude brain waves ever recorded during sleep or wakefulness. These massive neural events appear as dramatic spikes on electroencephalograms, reflecting moments when millions of neurons briefly synchronize before falling quiet. Neuroscientists believe these waves may serve as sleep's protectors, actively suppressing disruptive stimuli while simultaneously participating in memory consolidation. Though we experience nothing of these electrical storms, they may represent the brain's most profound, coordinated activity. Like lightning that momentarily illuminates an entire landscape before returning it to darkness, K-complexes briefly reveal the vast synchronized potential of the sleeping brain. Dreaming emerges from an ancient chemical tide. During REM sleep, The cholinergic system, one of the brain's oldest neurotransmitter networks, surges into activity, facilitating both vivid dreaming and memory consolidation. These specialized neurons release acetylcholine throughout the cortex, temporarily activating visual processing regions despite closed eyes. Researchers tracking this system have documented how blocking these receptors dramatically reduces dream recall and impairs certain forms of memory. The evolutionary conservation of this mechanism across species suggests its fundamental importance to brain function. Like an ancestral rhythm that continues echoing through time, this neurochemical pattern has accompanied sleep through millions of years of evolution, quietly shaping the dreaming mind. Sleep maintains its own internal economy of time. Sleep efficiency, calculated as time actually asleep divided by total time in bed, averages between 85 to 95% in healthy young adults. This ratio reflects how effectively the brain transitions into and maintains the sleep state without unnecessary interruptions. Sleep scientists use this metric as a window into sleep quality, noting how it tends to decrease with age and certain disorders. Optimal efficiency suggests a brain that slides easily into unconsciousness and remains there until the appropriate waking time. The remaining percentage, those brief awakenings we rarely remember, may serve as important monitoring periods, maintaining sleep safety while preserving its restorative benefits. Light speaks directly to the brain's inner timekeeper. The suprachiasmatic nucleus receives illumination information through specialized retinal ganglion cells containing melanopsin, creating a dedicated pathway separate from the visual system. These unique photoreceptors respond specifically to blue wavelengths, allowing the brain to distinguish daylight from artificial sources. Research has revealed how these cells connect directly to the brain's master clock, without processing through visual centers. This explains why even some blind individuals maintain circadian entrainment despite lacking conscious sight. In the complex relationship between environment and internal time, these specialized messengers translate the language of photons into the dialect of neural timing. Their quiet signals, synchronizing biology with astronomy. Waves of different frequencies dance together in the sleeping brain. Slow oscillations during deep sleep coordinate the precise timing of sleep spindles and hippocampal sharp wave ripples, creating a three-part harmony of neural activity. This remarkable synchronization allows information to flow between brain regions in carefully timed packets. Neuroscientists recording these patterns have discovered how the slowest waves seem to conduct the timing of faster oscillations, like a conductor setting the tempo for different sections of an orchestra. This temporal coordination appears essential for memory consolidation and synaptic homeostasis. In the quiet theater of the sleeping brain, these rhythms perform their nightly concert, each wave rising and falling in precise relationship to the others. Pain's messenger falls silent during deep sleep. The anterior cingulate cortex, a region central to pain perception, maintains reduced activity during non-REM sleep, explaining our decreased sensitivity to discomfort during slumber. Brain imaging studies reveal how this area, normally responsive to painful stimuli during wakefulness, becomes significantly less reactive during deep sleep stages. This dampening mechanism allows minor injuries or chronic pain conditions to fade from awareness during rest. Though the body's pain receptors continue functioning, the brain regions that interpret their signals temporarily reduce their vigilance. Like a telephone that continues ringing in an empty room, pain signals may continue arriving. but the receiver has temporarily stepped away from the desk. The sleeping brain perfects what the waking mind has practiced. Sleep-dependent learning shows improvements of 15 to 20% in motor skill tasks following adequate slow-wave sleep, revealing night's hidden role in mastery. Researchers testing performance before and after sleep consistently find these surprising gains occur without additional practice. The enhancement appears particularly pronounced for procedural memories involving movement sequences or musical performance. This overnight improvement suggests the brain continues refining neural pathways during unconscious hours, silently strengthening connections established during daytime learning. Without awareness or effort, sleep transforms tentative abilities into more fluid execution. Like a sculptor who returns to find clay mysteriously refined in their absence, we awaken to discover our skills subtly transformed. Chemical tides ebb and flow beneath dreams. The RAFE nuclei, containing the brain's primary serotonin neurons, reduce their firing rates by 50 to 90% during REM sleep compared to wakefulness. This dramatic decrease in an otherwise stable neurotransmitter system creates unique neurochemical conditions during dreaming states. Researchers measuring this fluctuation have correlated it with certain dream qualities, particularly their emotional intensity and unusual narrative structure. The temporary absence of this stabilizing influence may explain why dreams often contain improbable scenarios or violations of natural laws. In the delicate chemistry of consciousness, serotonin's retreat creates space for other voices to emerge, allowing the dreaming mind to explore realities typically filtered by waking reason. The sleeping body enters a state of relative calm. Sympathetic nervous system activity, our fight or flight response, decreases by 10 to 30% during non-REM sleep compared to quiet wakefulness. This reduction creates the physiological conditions necessary for bodily restoration and energy conservation. Scientists measuring heart rate variability, blood pressure, and stress hormone levels have documented this shift toward parasympathetic dominance during deeper sleep stages. The resulting decrease in metabolic rate allows resources to be redirected toward growth and repair, rather than readiness for action. Though occasional surges occur during dreams, the overall pattern favors restoration over responsiveness. Like a city gradually dimming its lights as evening progresses, the body reduces its state of alertness as sleep deepens. New neurons are born while consciousness sleeps. The brain continues producing fresh cells in the hippocampal dentate gyrus through adult neurogenesis, a process that accelerates during certain sleep stages. This remarkable ability to generate new neural tissue, once thought impossible in adult brains, appears particularly active during periods of deep sleep. Researchers tracking cell division markers have found that sleep deprivation significantly impairs this regenerative process. These newborn neurons eventually integrate into existing memory circuits, supporting learning and cognitive flexibility. Though we remain unaware of this cellular renewal, it represents one of sleep's most profound contributions to brain health. Like seeds sprouting beneath snow, new neural possibilities quietly emerge during the mind's winter. Sleep pressure builds with mathematical precision in the waking brain. Mediated by adenosine accumulation, this pressure increases exponentially when wakefulness extends beyond 16 hours, creating an increasingly urgent biological drive for rest. Scientists measuring cognitive performance can predict impairment curves that closely match this exponential function. The system ensures that the longer we remain awake, the more powerful sleep's pull becomes, eventually rendering continued consciousness nearly impossible. This elegant self-regulating mechanism prevents excessive sleep deprivation under normal conditions. Like gravity's invisible but irresistible force, sleep pressure silently accumulates until it eventually pulls consciousness back to Earth, regardless of our intentions to remain aloft. Visual signals fade at the threshold of perception during sleep. The lateral geniculate nucleus gates information processing during slumber, preventing external visual input from reaching consciousness despite the brain's continued activity. This selective filtering explains why we can sleep with eyes occasionally open, yet perceive nothing of our surroundings. Researchers studying this mechanism have discovered how this gateway structure actively suppresses signals from the retina while still allowing internally generated imagery during dreams. This disconnection between external reality and internal experience creates the conditions necessary for the dream world to unfold undisturbed. Like a theater that closes its doors to outside light so the projector's images can appear on screen, the sleeping brain creates darkness for its own internal cinema. Waves of neural silence travel across the sleeping brain like weather systems. Cortical slow waves propagate at speeds of 1 to 7 meters per second during deep sleep, creating moving patterns of activity and inactivity across the brain's surface. Researchers using high-density electroencephalography can actually track these waves as they spread from their points of origin. These coordinated oscillations appear essential for memory processing and cellular recovery, their rhythm creating windows of opportunity for specific restoration processes. Though imperceptible to the sleeper, these waves represent one of the brain's most coordinated large-scale activities. Like ripples moving across a dark pond, these oscillations travel silently through neural tissue, their passage temporarily restructuring the electrical landscape of thought. Growth emerges from the deepest valleys of unconsciousness. Sleep-related hormone release includes growth hormone peaks occurring within the first 3 hours of sleep, coinciding precisely with the night's deepest slow-wave periods. This carefully timed surge supports tissue repair, cell regeneration, and metabolic regulation throughout the body. Researchers measuring hormone levels find this release follows a remarkably consistent pattern, with nearly 80% of the daily output concentrated in this early sleep window. The synchronization of hormonal and neural rhythms suggests an elegant coordination between brain states and bodily restoration. In the quiet beginning hours of each night, as consciousness retreats to its greatest depth, the chemistry of renewal quietly activates its ancient protocols. Consciousness requires integration that sleep temporarily dissolves. The claustrum, a thin sheet of neurons involved in awareness coordination, shows dramatically reduced activity during non-REM sleep stages. This small but crucial structure normally helps synchronize information across brain regions, creating coherent experience from separate sensory streams. Researchers studying this region have noted its central role in maintaining unified consciousness during wakefulness. Its deactivation during sleep may explain the fragmented nature of mental activity during non-dreaming states. In the intricate architecture of awareness, this structure serves as a keystone. When its function diminishes, the arch of consciousness temporarily collapses, allowing the mind to enter states incompatible with integrated experience. Sleep compresses time for the learning brain. Memory reactivation during slumber occurs at frequencies 6 to 12 times faster than the original learning experiences, allowing efficient review of daytime events. Using sophisticated recording techniques, Neuroscientists can identify these accelerated replay sequences in the hippocampus during specific sleep stages. This temporal compression explains how the brain can consolidate hours of experience during limited sleep periods. The mechanisms determining which memories receive this high-speed review remain incompletely understood. Like watching a film in fast forward, while somehow retaining all essential details, the sleeping brain rapidly scans its recent acquisitions, strengthening some while allowing others to gradually fade from its archive. The sleeping body maintains its delicate thermal balance. Though brain temperature drops slightly, thermoregulatory responses continue functioning during sleep, albeit with reduced sensitivity to ambient temperature changes. This carefully calibrated system ensures core temperature remains within safe ranges despite our unconscious state. Researchers studying this process have documented how the threshold for responses like shivering or sweating shifts during different sleep stages. This adjustment allows deeper sleep to proceed undisturbed by minor environmental fluctuations, while still protecting against dangerous temperature extremes. The body navigates this balance between responsiveness and rest throughout the night, like a carefully adjusted thermostat that allows some variation but prevents dangerous extremes. Sleep's regulatory systems remain partially active even as consciousness retreats. Electrical rhythms of consciousness persist in the dreaming mind. Gamma oscillations, ranging from 30 to 100 Hz, continue during REM sleep and correlate directly with dream vividness. These fast brain waves, typically associated with active perception and attention during wakefulness, suggest the dreaming brain engages similar mechanisms when generating internal experiences. Neuroscientists measuring these oscillations have found their intensity predicts the detail and emotional impact reported in dream journals. The presence of these high-frequency patterns during REM sleep provides a neural signature of dream consciousness. Like the rapid vibrations of violin strings creating rich tones, these swift oscillations may generate the textured quality of dream experience, their frequency determining how real our night visions appear. Beneath the master clock lies a secondary timekeeper. The subparaventricular zone coordinates multiple circadian rhythms, receiving signals from the suprachiasmatic nucleus and relaying timing information to systems controlling body temperature, hormone release, and sleep-wake transitions. This relay station ensures that diverse biological processes maintain appropriate temporal relationships with each other. Researchers studying this region have documented how its specialized neurons contain receptors for multiple neurotransmitters involved in sleep regulation. The evolutionary preservation of this structure across species suggests its fundamental importance to temporal coordination. Like a distribution center receiving deliveries and sending them to specific destinations, this neural region ensures timing information reaches the body's many rhythmic processes. Sleep transforms impossible puzzles into solvable problems. Sleep-dependent insight formation shows success rates increasing by an astonishing 250% following REM sleep periods, suggesting dreams restructure information in ways consciousness cannot. Researchers testing this phenomenon present subjects with seemingly unsolvable problems, finding dramatically improved solution rates after dream-rich sleep. This enhancement appears most pronounced for challenges requiring unconventional perspectives or creative connections. The mechanisms behind this transformative process remain mysterious, though they likely involve the brain's unique chemical and electrical environment during REM states. In the gentle alchemy of dream sleep, rigid mental frameworks dissolve, allowing new patterns to emerge from the fluid recombination of previously fixed elements. life's essential rhythm continues while consciousness sleeps. The medulla oblongata maintains critical autonomic functions, including breathing and heart rate regulation throughout all sleep stages, ensuring survival during our vulnerable unconscious hours. This ancient brain structure contains neural circuits that operate independently of higher awareness, governing the body's most fundamental processes. Scientists studying these mechanisms have identified specialized neurons that continue firing with remarkable consistency regardless of sleep depth. The reliability of these systems represents one of evolution's most essential adaptations, allowing complex brains to safely disconnect from external awareness. Like a ship's engine room that continues functioning while passengers sleep in their cabins, the medulla's tireless activity supports life's journey through unconscious waters. Chemical messengers flood the dreaming brain with strange wakefulness. Acetylcholine levels in the cortex during REM sleep exceed even waking levels by 10 to 40%, creating a paradoxical state of internal arousal during external stillness. Researchers measuring this neurotransmitter have documented its surge precisely when dream activity appears most vivid and emotionally charged. This cholinergic bath activates visual processing regions despite closed eyes and stimulates memory circuits without external input. The resulting neurochemical environment explains the hallucinatory yet meaningful quality of dreams. Like invisible ink, revealing hidden messages under special light, acetylcholine illuminates neural pathways normally traversed only in wakefulness, allowing consciousness to wander internal landscapes while the body remains safely at rest. Sleep's continuity holds the key to its power. Fragmentation, the breaking of sleep into shorter segments, reduces overall efficiency and increases stress hormone cortisol levels by 20 to 50% compared to consolidated rest. Each interruption, however brief, disrupts the natural architecture of sleep stages and prevents the deepest restorative processes from completing. Researchers measuring this effect find even unconscious micro-awakenings can significantly diminish sleep's benefits. The resulting elevation in stress, biochemistry, creates a harmful cycle, as cortisol itself further disrupts sleep quality. Though we rarely remember these fragmentations, their cumulative effect gradually erodes both body and mind. Like a symphony repeatedly interrupted mid-movement, fragmented sleep cannot deliver its full restorative composition. While consciousness rests, cellular renewal accelerates. The sleeping brain exhibits increased expression of genes involved in restoration and synaptic plasticity, activating molecular machinery that repairs daily damage and reorganizes neural connections. Researchers analyzing brain tissue have identified hundreds of genes whose activity changes dramatically between wakefulness and sleep. This genetic shift explains how sleep can simultaneously strengthen important memories while allowing less significant ones to fade. The coordinated activation of these restoration pathways requires the unique neurochemical environment that only sleep provides. Though invisible to observation, this molecular industry represents perhaps the most fundamental purpose of sleep. Like a forest growing in silence, the brain renews itself through countless microscopic processes, while thought's usual pathways lie quiet. The sleeping brain maintains selective attention amid unconsciousness. Sensory gating during sleep allows processing of relevant stimuli, while filtering out irrelevant environmental noise, creating a remarkable form of unconscious discrimination. A mother wakes to her baby's cry but sleeps through traffic noise. A person responds to their name but ignores conversation. Researchers studying this phenomenon have documented how emotional significance and personal relevance determine which sounds penetrate sleep's protective barrier. This elegant filtering system allows the brain to maintain awareness of potential threats without sacrificing restorative depth. Though we experience nothing of this ongoing evaluation, it represents one of sleep's most sophisticated functions. Like an invisible guardian sorting through countless signals, sleep preserves its essential qualities while remaining responsive to what truly matters. Dreams unfold in a realm free from external control. The locus coeruleus norepinephrine system's complete inactivity during REM sleep enables memory consolidation without interference from ongoing sensory input or conscious manipulation. This specialized neural network, normally responsible for attention and arousal, falls utterly silent during dreaming phases. Researchers measuring its activity have documented this remarkable shutdown, which occurs nowhere else in normal brain function. The resulting neurochemical environment allows the brain to process experiences according to internal associations rather than external logic. In this strange absence of norepinephrine, memories reorganize themselves following emotional and symbolic connections that consciousness might never discover. Like stars becoming visible only when daylight fades, certain neural relationships emerge only when the brightness of norepinephrine dims. Breath itself transforms during unconscious hours. Sleep-related breathing changes include reduced respiratory rate and increased reliance on the diaphragm rather than chest muscles, creating a more efficient oxygen exchange. This subtle shift toward deeper, slower breathing supports the lower metabolic demands of the sleeping body while maintaining adequate oxygenation. Researchers measuring these parameters have documented how respiratory patterns change across different sleep stages, becoming most regular during deep, slow-wave periods. These alterations in breathing mechanics represent one of sleep's oldest evolutionary adaptations, preserved across countless species. Like tides that rise and fall with ancient rhythm, breath continues its essential movement through unconscious hours, its pattern reflecting the mind's changing depth beneath awareness. In the quiet rhythm of night, a gentle electrical pattern emerges. The thalamic reticular nucleus generates sleep spindles through rhythmic bursting at frequencies of 12-16 Hz, weaving a protective curtain around your slumbering consciousness. These brief oscillations shield your mind from disruption, allowing restoration to unfold undisturbed. They appear on brainwave recordings as delicate spindle-shaped patterns, each lasting only a second yet performing vital work. You may never witness these silent guardians of your rest, but they faithfully serve your sleeping mind night after night. Within their rhythmic pulse, your memories find safety to reorganize and strengthen. Each spindle represents thousands of neurons singing together in perfect harmony, a lullaby written in the language of electricity. Your body keeps an exquisite ledger of rest and wakefulness. Sleep debt accumulates with precision, requiring approximately 1 hour of additional sleep for every 2 hours of deficit incurred. This biological accounting explains why a weekend of extra rest cannot fully repay a week of short nights. Your brain maintains this balance sheet with remarkable accuracy, prioritizing deeper sleep stages during recovery periods to maximize restoration. We often treat sleep as negotiable, yet the mind's requirements remain steadfast. There is wisdom in honoring this rhythm, in recognizing that your consciousness requires regular renewal. Like a garden that needs consistent tending, your mind flourishes when given the steady care of sufficient rest. As you drift into deepest sleep, your awareness of your inner body gently recedes. The insular cortex, responsible for sensing your internal landscape, maintains reduced activity during deep sleep, creating a temporary disconnect from bodily sensations. This neural quieting helps explain the profound sense of physical dissolution that precedes dreams. During these hours, you are briefly released from the constant stream of internal signals, hunger, discomfort, tension that accompany waking life. This respite from bodily awareness creates space for more essential maintenance processes to unfold undisturbed. In sleep's embrace, you are momentarily freed from the physical self, floating in a realm where restoration happens beyond conscious perception. Sometimes, the boundary between dreams and movement blurs unexpectedly. REM sleep behavior disorder affects approximately 0.5% of people, causing them to physically act out dream content rather than maintaining normal sleep paralysis. Their bodies respond to dream scenarios, running, fighting, speaking, while consciousness remains suspended in sleep. This rare condition reveals the intricate balance between neural systems that normally keep us safely immobile during dreams. For those affected, the dream world leaks into physical reality in surprising ways. Though uncommon, this disorder reminds us of the delicate architecture that separates inner experience from outer action during our nightly journeys, and how beautifully this system typically functions for most of us. While you rest, a molecular shield forms around your cells. The sleeping brain exhibits increased production of antioxidant enzymes that protect against the cellular damage accumulated during waking hours. This quiet defensive system activates most powerfully during your deepest sleep phases, when consciousness has fully retreated. These protective molecules neutralize harmful free radicals, allowing cellular repair to proceed efficiently. You may not sense this microscopic vigilance, yet it faithfully preserves the very foundation of your health. Each night of sufficient sleep strengthens this invisible armor. In the serene darkness behind closed eyelids, your body works to maintain the delicate balance between damage and renewal that sustains life itself. Your sleeping mind cherishes emotional moments above all others. Sleep-related memory benefits show preferential enhancement for emotionally significant information over neutral content, suggesting that what matters most to your heart receives special attention in the night. This selective process helps explain why emotionally powerful experiences often remain vivid long after mundane details have faded. Your brain, in its wisdom, preserves what touches you deeply. There is profound efficiency in this system, honoring the experiences that shape your inner landscape, while allowing less meaningful details to softly dissolve. In the quiet laboratory of sleep, your memories are gently sorted by their resonance with your deepest self, a reminder that emotion guides what we become. Transitions between sleep's different landscapes require a skilled guide. The basal forebrain cholinergic system orchestrates these passages throughout the night, releasing carefully timed signals that shift your brain between different states of consciousness. This ancient neural system evolved long before human awareness, ensuring smooth passage through sleep's varied territories. Like a lighthouse keeper changing the signal as night progresses, these specialized neurons adjust their activity to illuminate different paths for your sleeping mind. You float between these states without effort or awareness, carried by biochemical tides that have flowed through countless generations before you. In this rhythmic alternation between different forms of unconsciousness, your brain finds renewal through variety. The architecture of sleep slowly transforms as we journey through life. Slow wave activity, the deepest form of sleep, decreases by approximately 8% per decade, beginning in early adulthood. This gradual shift explains why childhood sleep feels so profound and restorative, while older adults often experience lighter, more fragmented rest. Yet this change doesn't necessarily indicate dysfunction. Rather, it reflects the brain's evolving needs across different life stages. Our relationship with sleep transforms as we age. Like many of life's deepest experiences, there is a certain poetry in how our consciousness changes its relationship with rest, each stage of life offering its own unique pattern of connection with sleep's rejuvenating embrace. Even in deepest slumber, you remain connected to what matters most. The sleeping brain maintains selective attention to personally relevant sounds while filtering out background noise, creating a remarkable form of unconscious discernment. A mother wakes to her baby's soft cry but sleeps through traffic noise. You might respond to your name while ignoring conversation around you. This exquisite selectivity evolved to keep us safe, while allowing restorative sleep to continue uninterrupted. Your sleeping mind continues evaluating the world around you, maintaining just enough vigilance to protect what you value. In this balance between surrender and awareness, we find one of sleep's most beautiful paradoxes: complete rest alongside perfect responsiveness to what truly matters. Night after night, a gentle cleansing tide washes through your brain. Sleep-related protein clearance removes accumulated tau and amyloid beta proteins associated with neurodegenerative diseases, acting as a protective maintenance system. This remarkable process utilizes the brain's glymphatic pathways, which expand during sleep to allow more efficient removal of cellular waste. You experience nothing of this microscopic housekeeping, yet it faithfully preserves your cognitive health over decades. Scientists now believe this cleansing function may be one of sleep's most essential purposes, perhaps explaining why chronic sleep disruption increases risk for cognitive decline. In the quiet darkness, your brain bathes itself in healing fluids, a reminder that renewal often happens in stillness. As consciousness recedes, your sense of space dissolves into dream. The posterior parietal cortex, responsible for mapping your position in the physical world, shows reduced activity during sleep. This neural quieting helps explain the floating, unbounded quality of dreams, where normal spatial rules no longer apply. During these hours, your brain temporarily releases its grip on physical location, allowing consciousness to explore dimensions beyond ordinary reality. This liberation from spatial constraints creates the conditions where imagination can flourish without the limitations of physical laws. There is freedom in this nightly release from the constraints of position and boundary, a chance for your mind to experience existence beyond the physical coordinates that define waking life. Two ancient clocks govern your relationship with sleep. Sleep homeostasis involves complex interactions between circadian rhythms, your internal day-night cycle, and accumulated sleep pressure from adenosine building up during wakefulness. These complementary systems work in harmony, one measuring external time, the other tracking internal need. Together, they create the perfect moment when sleep arrives naturally and restfully. You exist at the intersection of these timekeepers, your consciousness rising and falling with their synchronized rhythms. There is profound wisdom in recognizing and honoring these biological patterns rather than fighting against them. In the space where these cycles align, your body finds its natural cadence of renewal. During sleep, your mind strengthens its inner connections while gently releasing the outer world. The sleeping brain exhibits enhanced connectivity within memory networks while reducing connections between distant brain regions, allowing focused internal processing. This shift explains how sleep simultaneously preserves important information while helping you detach from the day's experiences. Neural pathways carrying significant memories are repeatedly activated and strengthened, while less important connections gradually fade. You might experience this as the emotional distance that often develops between you and yesterday's concerns after a good night's rest. In sleep's embrace, your brain quietly reshapes its own landscape, deciding what to keep close and what to gently release into the past. Your dreams help process the emotions too complex for waking hours. Sleep-dependent emotional processing occurs primarily during REM sleep through intricate interactions between your amygdala, hippocampus, and cortex. During these periods, emotional experiences are reviewed in a neurochemical environment that allows integration without overwhelming stress. This explains why difficult situations often feel more manageable after a night of sufficient sleep. Your sleeping mind works to make peace with your emotional world, softening the sharp edges of difficult experiences. In the gentle darkness behind closed eyes, your brain creates space for emotional healing that the busy waking mind rarely allows, reminding us that rest itself can be a form of emotional courage. Your body temperature holds a key that unlocks the door to sleep. The preoptic area contains specialized thermosensitive neurons that promote sleep onset when your core body temperature decreases in the evening hours. These cells respond to the natural cooling that occurs as day transitions to night, helping synchronize sleep with darkness. The slight drop in temperature serves as a biological signal that prepares mind and body for rest. This explains why a cool bedroom often facilitates easier sleep than a warm one. There is ancient wisdom in this temperature-sensing system, connecting your sleep patterns to the natural rhythm of warm days and cooling nights that has shaped life on Earth since its earliest beginnings. Beneath the surface of sleep flows a rhythm older than consciousness itself. Sleep architecture demonstrates ultradian patterns, cycles within cycles, with predictable alternations between REM and non-REM states approximately every 90 minutes. These internal rhythms continue regardless of when you fall asleep or wake, suggesting they arise from fundamental neural oscillators deep within the brain. Your conscious experience of sleep may seem uniform, yet beneath awareness, these ancient cycles continuously unfold. Like ocean waves that have shaped shorelines for millions of years, before human eyes witnessed them. These neural rhythms have flowed through countless brains before yours, connecting you to life's most essential patterns of restoration. Even in profound unconsciousness, a quiet sentinel remains alert for danger. The sleeping brain maintains reduced but persistent monitoring of the external environment, preserving just enough awareness to respond to potential threats. This vigilance allows immediate awakening to smoke, unusual sounds, or signs of danger, while permitting deep restoration to continue undisturbed otherwise. There is profound evolutionary wisdom in this balanced system that has protected sleeping humans through countless generations. You rest each night within this protective awareness that you never consciously experience, yet depends upon for safety. In the vulnerability of sleep, your brain maintains just enough connection to the world to keep you safe, a hidden guardian watching over your dreams. As consciousness retreats, your body enters a state of quiet renewal. Sleep-related growth hormone release promotes tissue repair and influences metabolic processes throughout your entire system, with the highest concentrations occurring during the deepest sleep phases. This hormonal tide supports healing from the day's minor damages and maintains cellular health in ways that cannot occur during wakefulness. Children experience this regenerative surge most powerfully, explaining their remarkable capacity for growth and recovery. Though we sense nothing of this molecular restoration, it faithfully maintains the physical foundation of our existence, night after night. In sleep's gentle embrace, your cells remember how to heal themselves, a reminder that renewal often happens in stillness and darkness. During dreams, your mind temporarily releases its logical constraints. The dorsolateral prefrontal cortex, responsible for critical thinking and rational analysis, shows markedly reduced activity during REM sleep. This neural quieting explains why dream scenarios that would seem impossible during waking hours feel completely reasonable while dreaming. Without this brain region's reality-checking function, you accept flying, time travel, or conversations with the departed without question. There is creative potential in this temporary liberation from rational constraints, allowing connections that logical thought might never discover. In the gentle anarchy of dreams, your mind briefly experiences a different kind of consciousness, one where possibility expands beyond the boundaries of waking reason. Your need for sleep follows a predictable mathematical curve. Sleep pressure accumulation follows a saturating exponential function, reaching maximum levels after 24-30 hours of wakefulness. This means the longer you stay awake, the more powerful sleep's pull becomes, though eventually this curve plateaus. Scientists can predict performance impairment based on this function, mapping the precise relationship between wakefulness duration and cognitive decline. You exist within this mathematical reality, whether you acknowledge it or not. There is humility in recognizing these biological constraints rather than fighting against them. Like gravity's invisible pull, sleep pressure accumulates according to natural laws that have shaped life long before human will attempted to override them. In the quiet laboratory of night, your brain remembers how to grow. The sleeping brain exhibits increased expression of immediate early genes, involved in synaptic plasticity and learning, activating the very molecular machinery that allows neural connections to form and strengthen. This genetic activation occurs most intensively during specific sleep stages when consciousness has fully retreated. Without your awareness, the foundation for tomorrow's learning and adaptation is being quietly prepared. Each night of sufficient sleep supports this essential capacity for neural flexibility, maintaining your ability to adapt, learn, and evolve. In darkness and stillness, your brain whispers instructions to its cellular components, preparing for possibilities you have not yet encountered. Time itself shapes how sleep transforms learning into skill. Sleep-dependent skill consolidation shows optimal benefits when sleep occurs within 12 hours of initial learning, revealing a critical window for memory processing. This temporal relationship explains why learning something just before sleep often leads to better retention than the same practice followed by waking hours. Your brain's ability to convert experience into lasting ability depends on this relationship between learning and rest. There is practical wisdom in timing challenging learning experiences with your sleep schedule in mind. Like a photograph that needs time in developing solution, your experiences require the specific neurochemical environment of sleep to fully transform into enduring knowledge. A silent switch must be thrown for consciousness to surrender to sleep. The tuberomammillary nucleus histamine neurons cease firing during all sleep stages, facilitating the transition from alertness to slumber and helping maintain sleep once it begins. These specialized cells normally keep your brain in an awakened state, but their quieting allows consciousness to retreat. This neural silencing represents one of sleep's fundamental requirements, as histamine promotes the very qualities of awareness that sleep must temporarily suspend. You experience this transition as the gentle dissolution of active thought into floating imagery, and eventually unconsciousness. In this neural quieting, your waking self surrenders to sleep's embrace, releasing its grip on alertness and focused attention. Different regions of your sleeping brain communicate through synchronized rhythms. Sleep-related oscillations coordinate information, transfer between cortical and subcortical structures, creating windows of opportunity for memory processing and neural restoration. These rhythmic patterns, visible on brain recordings as waves of different frequencies, facilitate the precise timing required for complex sleep functions. Your unconscious experience of rest unfolds within these oscillating fields of neural activity, moving through different frequencies as the night progresses. Though you sense nothing of these electromagnetic symphonies, they provide the essential temporal structure that allows sleep's many functions to unfold in proper sequence. In these invisible rhythms, your brain finds the synchronization necessary for its most profound restoration. As you surrender to sleep, the executive command center of your brain gradually releases control. The sleeping brain demonstrates reduced functional connectivity in the executive control network compared to wakefulness, temporarily suspending the neural system responsible for planning, decision-making, and self-regulation. This network normally coordinates your most complex thought processes, but its quieting allows other brain systems to operate without interference during rest. You might experience this as the floating, directionless quality of thoughts that precede sleep. There is profound wisdom in this nightly release of control, a recognition that certain forms of restoration require surrendering the very mental faculties we value most during day. In letting go, your brain finds renewal that active control could never provide. The quality of your sleep might reveal something about your capacity for learning. Sleep spindle density, the number of these brief oscillations per minute, correlates positively with learning ability and resilience against external disruption. People who generate more of these electrical patterns typically form memories more effectively and maintain sleep more easily in noisy environments. These spindles represent synchronized firing between the thalamus and cortex, creating optimal conditions for neural plasticity. Though invisible to your awareness, these rhythmic patterns may reflect fundamental aspects of your brain's architecture and function. In the silent signatures of your sleeping brain, aspects of your cognitive potential express themselves night after night. The chemistry of reward transforms during your nightly journey through consciousness. The ventral tegmental area dopamine system, central to motivation and pleasure, shows reduced activity during non-REM sleep and increased firing during REM dreaming states. This fluctuation helps explain the emotionally neutral quality of deep sleep compared to the sometimes euphoric or frightening nature of dreams. Your brain's relationship with reward and desire shifts as you cycle through different sleep stages. There is balance in this alternation between neurochemical states, allowing periods of complete emotional neutrality to alternate with phases of intense emotional processing. In sleep's changing landscape, your relationship with wanting and feeling evolves through the night. Each night, your brain carefully preserves what matters from your day. Sleep-dependent memory consolidation systematically strengthens synaptic connections formed during wakefulness, focusing on those that represent significant information or skills. This selective reinforcement explains how important experiences become part of your long-term memory while trivial details fade. The process unfolds through precise coordination between hippocampus and cortex during specific sleep stages, requiring no conscious effort on your part. You may notice this process only in its results, the integration of yesterday's experiences into your ongoing sense of self. In sleep's gentle hands, your memories find their proper place in the continuous story of your life. The chemistry of your brain transforms in sleep's embrace. The sleeping brain exhibits altered neurotransmitter ratios, with decreased norepinephrine, serotonin, and histamine levels, creating a neurochemical environment utterly different from wakefulness. This shifted balance allows neural processes that cannot occur during normal consciousness, enabling the brain's essential maintenance operations. Your subjective experience of this chemical shift ranges from the floating sensation of sleep onset to the vivid imagery of dreams. There is necessity in this neurochemical alternation. Neither state alone could support life. Like day and night, these complementary neurochemical environments each contribute essential elements to your existence, reminding us that wholeness requires rhythmic change rather than constancy. Even your relationship with hunger changes as you sleep. Sleep-related hormone fluctuations include decreased leptin and increased ghrelin, subtly influencing appetite regulation even during unconsciousness. This explains why insufficient sleep often leads to increased hunger the following day. Your body's delicate hormonal balance has been disrupted. These chemical messengers flow through your bloodstream even as you dream, preparing your body for the energy needs of the coming day. You sense nothing of these molecular signals during sleep, yet they help shape your relationship with food upon awakening. In the invisible chemistry of night, your body prepares for tomorrow's nourishment needs, connecting sleep quality to the wisdom of appetite. Pain itself retreats in sleep's gentle presence. The cingulate cortex, a region central to pain perception, maintains reduced activity during deep sleep, creating natural analgesia that explains why discomfort often diminishes during rest. This neural quieting represents one of sleep's most merciful aspects, temporarily releasing you from physical suffering that might dominate waking awareness. The threshold for pain increases significantly during specific sleep stages, providing a respite from chronic conditions. There is compassion in this biological design that grants periods of relief even to those in physical distress. In the sanctuary of deep sleep, even pain loses some of its power, offering regular windows of peace in otherwise difficult journeys. Your sleep finds harmony in consistency rather than quantity alone. Sleep architecture optimization requires maintaining consistent timing within 30-60 minutes of the same schedule daily, allowing your circadian system to properly align with sleep pressure cycles. This regularity proves more beneficial than occasional long sleeps following deprivation. Your brain thrives on predictable patterns of rest and activity, using these rhythms to properly time countless biological processes. There is wisdom in honoring these natural cycles, rather than imposing irregular schedules that confuse the body's internal timing systems. Like a musician finding the beat, your brain functions best when sleep arrives in a consistent rhythm, creating a foundation of predictable renewal upon which health can be built. Your sleeping mind continues finding connections between seemingly unrelated concepts. The brain processes semantic relationships during sleep, forming remote associations between memories that might never connect during focused waking thought. This explains why solutions to problems often appear suddenly after a night of rest. Your brain has been quietly exploring connections without the constraints of directed attention. Creative insights frequently emerge from this unconscious processing that links distant concepts. There is a different kind of intelligence at work while you sleep, one that values unexpected connections over logical progression. In the wandering neural activity of the sleeping brain, your mind discovers hidden pathways between thoughts that daylight thinking might never reveal. Sleep represents one of your brain's most active and coordinated states. Far from passive unconsciousness, sleep requires precisely orchestrated neural activity across multiple brain systems and neurotransmitter networks. This sophisticated state evolved over millions of years, suggesting its fundamental importance to survival. Your experience of simply falling asleep belies the complex choreography of neural systems that must synchronize to create this state. What feels like surrender actually requires active participation from countless specialized brain regions working in harmony. In the apparent stillness of sleep lies one of your brain's most remarkable achievements, a carefully constructed state of consciousness, designed specifically for renewal, one that has sustained life through countless generations. As you drift closer to sleep, remember that your brain never truly rests. Instead, it shifts into a different mode of being, just as essential, just as remarkable as wakefulness. The thalamic nuclei will soon generate their rhythmic spindles. Your hippocampus will reactivate today's experiences, and billions of cells will coordinate in a symphony of restoration that has evolved over countless millennia. If you're still awake and want to learn more about the wonders of sleep, you can always drift into another episode. But for now, may your brain wave slow, your thoughts grow peaceful, and your consciousness gently dissolve into the embracing darkness of sleep. Good night.